Thanks for joining us, and welcome to today's Oracle Machine Learning Office Hours product overview, introducing Oracle Machine Learning for R for Oracle Autonomous Database. I'm Mark Hornick, and joined by Sherry LaMonica. So in this session, we're going to continue our series on Oracle Machine Learning for R on Autonomous Database with an introduction and demonstration of the now released product. I'll start off with an introduction to OML for R, and Sherry will walk through the OML for R features using OML Notebooks. As always, if you have questions, please post them in the Q&A, and we'll address them during the session or at the end. But before we get started, let's hear from you regarding your primary objective for today's session. Is your goal to learn about anything cool with respect to Autonomous Database? Or learn how to use R for in-database machine learning, get a deeper understanding of OML for R, or something else, which you can specify in the chat. So it seems like we've got certainly the interest in getting a deeper understanding of OML for R on Autonomous Database. Over half of the folks interested there. About a third are interested in learning how to use R for in-database machine learning, and some very interested in just cool new features for Autonomous Database. All right, well, thank you very much for participating in our poll, and we will continue. So OML for R was first released in 2011 for Oracle Database, and new in this release is OML for R version 2.0 for Autonomous Database. And in this part of the session, we'll discuss some of the issues with traditional R and data source interaction, give a brief overview of the Oracle Machine Learning product family, and then focus on features and functionality of Oracle Machine Learning for R. You should come away from this session with a decent understanding of the value that OML for R offers for exploring and manipulating database data, building models, and deploying R-based solutions. So my name is Mark Hornick with Oracle Machine Learning Product Management. Now, we're excited to announce that OML for R is now available on Autonomous Database. And combined with the SQL and Python APIs, the introduction of R further extends Autonomous Database as a platform for data science and machine learning. Users can now run R, SQL, and Python paragraphs in the same notebook, selecting the most appropriate language for a given task. So why is an R interface to work with database data important? Over the years, customers have shared various pain points when developing machine learning solutions using third-party tools. For example, some will say, it takes too long to get or to load data into those engines, or getting models into production takes too long, or it's complex. In other cases, there are concerns about data security, backup, and recovery, where data is pulled into non-secure environments. Still others will cite scalability and performance as a major concern, whether training individual models, using those models for inference, or dealing with hundreds or thousands of models in production settings. So let's talk about traditional R engine and data source interaction. Analyzing data using open source tools like R and other environments, where open source or proprietary often require enterprise users to request data extracts from data sources, load that flat file data in memory, and then push results back to the data repository. Other users may be able to extract data programmatically through various connectivity packages. For example, on Oracle Database with R, this is often R Oracle. However, pulling data programmatically has issues for larger data sets given internet bandwidth constraints. Overall, the challenges include data access latency, the need to change a language to access or manipulate data, or even more critically, the need for the full data set to reside in memory for analysis. In addition, most third-party packages are single-threaded, meaning that even if you have multiple processors available, scalability and performance will be severely limited. And when data is pulled from the database, there are of course issues for backup, recovery, and security. And for production deployment, there's the need to spawn analytical engines, load the data, and enable applications and dashboards to access the results. Now, this all adds up to unnecessary, or at least undesirable, complexity. So this is where Oracle Machine Learning comes in. Oracle Machine Learning is a family of components supporting data science projects. Oracle Machine Learning enables data exploration and preparation, and model building, evaluation, and deployment at scale. Oracle Machine Learning focuses on interfaces for three popular languages, as we've been saying: SQL, R, which is our focus today, and Python. OML for SQL provides a SQL interface to the in-database parallelized algorithms, which keeps data under database control. OML for R and OML for Py are the R and Python languages, language interfaces to the OML functionality. And for interaction with autonomous database, we provide OML Notebooks with the SQL, PL/SQL, Python, Markdown, and now R interpreters. The same notebook can contain paragraphs with each of these interpreters, which allows users, of course, to choose the most effective language. Now, Oracle Data Miner is a SQL developer extension that enables users to create, schedule, and deploy analytical workflows through a drag-and-drop user interface. It connects to both Oracle database and autonomous database instances. OML for Spark provides machine learning in the big data environment, such as Big Data Service, using an R interface to scale and with parallelized algorithms. Oracle Machine Learning AutoML UI is a no-code user interface that automates the model building, selection, tuning, and deployment process. And lastly, Oracle Machine Learning Services is a RESTful service for model deployment and management, along with cognitive text analytics. Users can deploy models from the AutoML UI directly to OML services in just a few clicks. So let's get a sense of which OML components you currently use or have at least tried. And if something else comes up, please specify that in the Zoom chat. So we're looking at here, SQL, Python, R, notebooks, or the AutoML UI. So we've got, let's see, 70%, 73% are using OML notebooks. OML for SQL at about 40%. OML for Py, another 40%. The AutoML UI, we've got about 15% there. And the same thing with OML for R. So this is really great to see that we've got such a range of folks leveraging this technology. Now, the SQL interface for in-database machine learning provides its foundation for the algorithms exposed in OML for R. And so it makes sense to say a few words about this interface first. The in-database parallelized algorithms keep data under database control, as we've been saying. There's no need to extract data to separate machine learning engines, which can be time-consuming and introduces problems related to data security, backup recovery, and stale data. The algorithms are fast and scalable. They enable batch and real-time scoring and provide explanatory prediction details so you can understand why an individual prediction is made. Now, the in-database machine learning models are first-class objects in the database. You can control access by granting and revoking permissions, audit user actions, and export and import machine learning models across databases. And this includes what we have for R and Python models built through those interfaces. Since OML for SQL supports the R interface, OML for R reaps the same benefits for in-database models. OML for SQL is at the core of OML's Bring the Algorithms to the Data tagline. So let's move on to OML's interface for R. Now, Oracle Machine Learning empowers data scientists with R by leveraging the database as a high-performance computing environment. Database tables and views are accessed through data frame proxy objects with overloaded functionality that produces SQL transparently behind the scenes. The in-database machine learning algorithms are exposed through a native R API, and these algorithms produce the same first-class in-database machine learning models as the SQL API. You can also store and manage R objects, like R machine learning models, directly in the database using the data store feature. And this avoids, if not eliminates, the need to manage flat files. You can create user-defined R functions and manage them in the database script repository. And you can invoke these user-defined R functions from SQL and on autonomous database, also from REST endpoints. There's no need to provision separate R engines for solution deployment. OML for R provides all the needed infrastructure. Now, OML for R functionality is characterized by three functional areas. Using proxy objects, the transparency layer allows users to operate on database data using familiar R syntax, overloading functions that operate on, for example, data frame proxy objects. These functions construct SQL for in-database processing. Results are typically returned as proxy objects as well, and this enables scalability. The in-database algorithms are exposed through convenient R interfaces that use the R formula specification for predictors and targets. And through embedded execution, user-defined R functions can be invoked on database environments spawned and controlled R engines. Now, embedded execution enables data parallel and task parallel processing. For example, an open source model can be scaled to large volumes of data for making predictions by requesting that multiple engines be spawned to process chunks of data in parallel. OML provides the supporting infrastructure to simplify and automate this process. So, which OML for R feature areas are you most interested in? Please select all that apply. Is it the transparency layer, the in-database algorithms, embedded R execution, the data store, or the script repository? Wow, so we're at 100% so far saying the in-database algorithms, down to, 75% now. Transparency layer at about a quarter. Embedded execution is also around a quarter. The data store and script repository have about 20%. Okay, so I think that we're holding steady there at the vast majority want OML for R to access the in-database algorithms, followed by the transparency layer and embedded execution. All right, well, thank you for that feedback. So Oracle Machine Learning is the only machine learning toolkit specifically designed to take advantage of the real application clusters and Exadata platforms. Optimizations include in-database algorithms that leverage distributed parallelism and scalability across cluster nodes. Both autonomous database and on-premises Oracle database instances reap these benefits. Now, OML algorithms operate beneath the Oracle database security layer, something that only OML can do by virtue of being part of the core database software. Scoring takes advantage of function pushdown to process data at the storage tier, a unique Exadata feature, and this makes scoring that much more scalable and performant. One of the challenges with some other ML platforms is the need for data to fit in memory. And with OML, data is brought into memory incrementally as needed. Further, models are cached and can be shared across queries. OML leverages disk-aware structures, relying on the database memory manager for efficient allocation in multi-user environments. Now, a brief comment about OML for R for Oracle Database and Database Cloud Service installations. Users typically install R and the OML for R server components on each node of a real application cluster server, such as an Exadata. To use third-party packages with embedded R execution with Oracle Database, these must be installed on each node in the cluster as well. In Autonomous Database, OML for R is pre-installed and pre-configured, so you can just start using it. So how do we achieve scalability through OML for R? OML for R introduces proxy objects, as we've mentioned a couple of times now, and these behave as R data frames, but map to database tables and views. Here we show how the ORE frame, which serves as a proxy for database tables and views, is a subclass of R's data frame class. Note that the structure of the R data frame, which contains the actual data, is very different from the proxy object, which contains a reference or query to the data table or view. As we're showing here, this depicts the query that corresponds to the iris table in the database. You'll notice some of the columns like sepal length and sepal width mentioned in the query. To give you a clearer idea of what we mean by the transparency layer, we use proxy objects and overloaded functions to take advantage of database column indexes, query optimization, parallelism, and even table-level partitioning. The use of proxy objects and overloaded functions can greatly improve performance and scalability on database table operations, since the data is not brought to the client engine. There are several ways to get proxy objects. We can create a table from an R data frame using ORE create. We specify here the data frame iris and the table name that we want to use. To create a temporary table that's automatically reclaimed when the database connection ends, we can use ORE push. And if the table already exists in the database, the most likely case, we can use the function ORE sync and specify the table name we wish to access. Each of these returns a proxy object that we can then use to invoke familiar R functions like dim, head, and summary. And these overloaded functions, in effect, translate the desired functionality to SQL for in-database processing as appropriate. Now, just for reference, here's a mapping between R data types and the database. The OML for R mapping follows that of the R Oracle package. Now, for example, if the database has a column of type date or timestamp, this is mapped to R's POSIX-CT data type. And if an R data frame has a column of type POSIX-CT or date, this gets written to the database as type timestamp. Now, also for your reference, the first release of OML for R on Autonomous Database supports these packages. And later this year, we'll be adding the capability to add user-specified third-party packages as well with Autonomous Database. Users can leverage a variety of in-database machine learning algorithms from R, and this is the set of machine learning techniques and algorithms supported in OML for R on Autonomous Database. And during the demonstration, you'll see a code example of one of these. Note that users can also take advantage of automatic data preparation, partitioned model ensembles, and integrated text mining. And if you're interested, we have example notebooks on Autonomous Database and our GitHub repository that highlight each of these. So let's take a look at the embedded R execution feature from the R and SQL API perspective. We'll illustrate model building and then data parallel data scoring using the model that we just built. So here's the code that builds a linear model, storing it in the database using the data store, while having the database spawn and manage the R engine to process it. Our user-defined function, or UDF, builds a model to predict species using a data frame passed as the first argument, dat. And it saves this model to the database in a data store using ORE save. The return value from our function is simply a Boolean true. Next, we create our UDF in the script repository and get a proxy object to the iris table. Then we invoke table apply. We provide the proxy object iris, the name of the function in the script repository, the name of the data store under which we'd like to store this model, and to automatically connect to the database from the spawned R engine to access the data store. The database environment spawns an R engine and loads the user-defined function and the iris data. When finished, we have our model saved in the database and the R engine is released. Now we can invoke that same UDF from SQL, say to allow our application to easily invoke this function. We use the RQ_TableEval database table function since we want to operate on the dataset all at once. Of course, there are considerations for scalability when taking this approach, and that's a topic for another day. In the first argument to RQ_TableEval, we specify the source data table named iris. We specify the function arguments as a JSON string of name-value pairs, which includes the name of the data store, and that we want to use the Autonomous Database medium service level to enable parallelism. We indicate that the output format of the result should be an XML string. Recall that we're just returning the value true from our function. And lastly, we give the name of our UDF that we just created in the script repository. Now, with the model created and stored in the database, let's define a function that uses that model to make predictions. We load the model from the data store, make the predictions, and return the actual and predicted results. As before, ORE script create stores the UDF in the script repository. And we can also store our UDF using PL SQL with the function RQ_script_create. And this supports DBAs or SQL users to receive UDFs from R developers to deploy themselves, perhaps in secure production environments. So now let's use OML for R to get data parallel behavior using our scoring UDF. After getting a proxy object to the iris table, we provide it to ORE row apply, along with the name of the function in the script repository, and that we want 10 rows to be processed at a time, and do this in parallel using 4 R engines. The fun value parameter specifies the resulting data frame structure, so it can be automatically created as a single result, as opposed to a list of partial results. Invoking row apply causes the database to spawn the R engines, load the UDF and a data partition into each, and then collect the results, which are presented as a single ORE frame proxy object. And this is important since results themselves can be large. We don't want to pull results to the client unnecessarily. Next, we'll create the table batch scores and use the overloaded R table function to compute the confusion matrix in the database on the batch scores proxy object. And note that only the confusion matrix itself will be returned to the client without the need to load large volume data to the R client engine to do that processing. Now here's the corresponding SQL invocation using RQRowEval on Autonomous Database. We have the data table name iris, our parameter list is a JSON string, which specifies the medium service level, and that parallelism should be enabled. We specify the output format indicating the structure of the result to be returned, and in the row num argument, we indicate that 10 rows should be processed at a time in each invocation, and the source name argument to specify the UDF in the script repository is named score data. So in a moment, Cherry will also highlight the REST interface that's available on Autonomous Database. Before we get to the demonstration, let's touch briefly on the compute resources on Autonomous Database for OML for R. And the same also applies to OML for Pi. Now, parallelism with embedded R execution is tied to the Autonomous Database autoscale feature. When autoscale is enabled, users can use up to 2 times the base OCPU specified for the database. Each VM allows up to 8 OCPUs, and there are a maximum of 5 VMs per tenant supported. So let's illustrate with an example. Suppose we have an Autonomous Database instance provisioned with 8 OCPUs. This will allow 2 VMs to run containers for a total of 16 OCPUs with autoscale. The high service level allows an individual embedded execution call to use a maximum of 8 OCPUs, which is also the maximum for the VM. And 3 such calls can run concurrently. The medium service level reduces to 4 OCPUs, but can allow up to 20 concurrent invocations. And the low service level allows for 1 OCPU and up to 100 concurrent invocations. So now I'll turn the screen over to Sherry LaMonica, who will take us through OML for R on Autonomous Database using the OML Notebooks interface. Sherry, it's all yours.
Okay, thank you, Mark. Okay, so here you're looking at OML Notebooks on Autonomous Database. So we'll start with the transparency layer. The first thing that we need to do is load the ORE library, and ORE stands for Oracle R Enterprise, which is the original name for this product. Next, we create a database table from an R data frame, and we get back a proxy object in our R environment. We use the ORE create function to create a table in the database using the iris data frame. And after we create this table, we have an ORE frame with 150 rows and 5 columns. We can list the objects in our environment by invoking ore.ls. Using the overloaded call names function, we can see the columns in our iris table and the first few rows of the data set using the overloaded head function. And then we can use the overloaded summary function to compute statistics inside the database so that no data needs to be retrieved to the client except for the summary statistic values themselves. We can also pull the iris database table back to our R client, and we get back on our data frame. Now here we're comparing the structure of the local iris data frame to the ORE frame proxy object, and the underlying structure is different. If you look at the data query slot, you can see the underlying query that corresponds to that table. And then using standard R syntax again, we can select specific columns for our ORE frame proxy object. We can select columns using column indexes, and we can also exclude columns using column indexes. And we can filter rows and columns using familiar R syntax on the ORE frame object. Here we have sepal length greater than 5 as the first example. Okay, so we can also use the overloaded dplyr functions to operate on ORE frames. And here we load the magrittr library and ORE dplyr, so we can select and exclude columns and filter rows along with other functions that are provided with the ORE dplyr package. Moving on, we can join data if we create local data frames, and running the local R merge function, we can see the result of the merge. We can also create tables in the database using ORE create, as we did earlier. And we can invoke merge on the ORE frames that result from that. And we get the same result, but you'll notice it is in a different order. And that's because row ordering is not automatically happening. And this is because sorting is expensive, especially as the data volumes increase. We can store objects in the database data store. And in this case, we're going to save the R data frame iris in a data store called My Data Store. We create a list of values A, B, and C, and we'll save that in the same data store. And then peeking at the data store that we just created, it shows that we have two objects, the iris data frame and our list, when it was created and its size. And we can also see the contents inside of My Data Store as well. And here we see iris with the class data frame and the list object, its class and size. And then here are a few examples of overloaded graphics functions, box plot and histogram. You can see that they're using the iris proxy data frame object. So that's the transparency layer. The next area that I wanted to go into a little more detail is machine learning. So in this example, we're building an in-database random forest model to predict species, and we'll get back a model proxy object. We're using the standard R syntax, and if you notice, also the standard R formula syntax. We're getting the summary of the model. We see the settings that were used, and also the attribute importance ranking for the predictors. We can also use this in-database model to make predictions using the model proxy object. We're asking for the final prediction along with the probability of each of the other classes that could be predicted, and we specify a supplemental column, species, to be returned in the final result, and this is the original target value. We can also save our model proxy object to the data store. And so now we have three objects in My Data Store, the model that we just built, the iris data frame, and the list. Okay, now let's take a look at embedded R execution. So the first thing we do is just define an R function, and this function is going to plot n random red dots and return a 2-column data frame. And then we run that user-defined function directly here in the local R engine, and we see that the data frame is returned along with the plot of the random red dots. So now let's do the same thing using embedded R execution using ORE doEval. So we're going to run our user-defined function in a database spawned engine. We'll pass the name of the user-defined function along with our arguments, and we get the same result. We can also store the user-defined function in the database R script repository and then run that named user-defined function in the data store. And what happens is we run the named user function in a database spawned R engine, and we pass the function name and arguments again with the same result. Here we're illustrating using OML for R with data parallelism, and we're building one linear model per species. This is using the ORI group apply function, where we pass in our proxy object, iris, the column that we wish to partition the data on, which is species, that we want to build one linear model to predict sepal length given the other predictor values, and that we'd like to use two parallel R engines. And what this does is it spawns the two parallel R engines and feeds the data into each one as it's processed, collects the results, and returns them back to the client. And in this case, we see that we have the model for each category of the species variable returned: Setosa, versicolor, and virginica. As Mark mentioned, we also have a SQL API for embedded R execution. In order to use the SQL API for embedded R execution, the function has to have been saved by the user in the script repository. And then you need to get an access token to be able to use these functions within your OML notebook. And we'll show you how to do that here. I make a note here about the supported output format. So we support JSON output, XML, PNG, relational output, and asynchronous mode. And we'll go over an example of each. So the first thing we do is we use this helper function to get your access token. And this function has three inputs: your OML URL, which you can get from database actions, your OML username, and password. And this goes out and it fetches that function, and we are saving it into a database table along with the user credentials just for ease of use. So when you use this, you would just enter your URL, username, and password here. And then we have these functions to define or set the function in your session. So RQ set auth token will set the token in a token store for use with your OML notebook, and RQ token is set will just verify that everything is set and working correctly. And the token is valid for an hour, and it can be extended for up to 8 hours. So here we are setting the token and confirming that it is indeed set. So now that you've set your token, you're ready to use the SQL API for embedded R execution. And in this case, I'm using RQFL2, which is not parallel enabled. It's for serial execution only. So we're using the ORI service level low, and specifying that we want JSON output. And then we provide the script name that is saved in the script repository, random red dots. And this is a portion of the output that you'll get. For PNG output, it's very similar, except we specify the output format as PNG and set the ORI graphics flag to true. It's false by default so that we can return those PNG image bytes. For XML output, again, we specify the output format as XML, the ORI service level is low, and the script name random red dots. If you'd like graphical output along with the XML output, you can also set the ORI graphics flag to true. And for relational output, in the out format, we are setting the output format that we desire, which is two columns, the ID and val columns, which are both number types. We specify their column name and their types. For asynchronous mode output, you can run your function in the script repository asynchronously, which then runs as a job, and that job can be polled using the functions RQ job status and RQ job result. And RQ job status will check and see, is my function still running, or is it finished, and can I go check the results? And then RQ job result helps you go and fetch the results. So the first thing that you do is submit the asynchronous job. And what you're going to do is set the out format to null for XML type outputs. And I've set ORI async flag to true to enable the asynchronous job to kick that off. And then, of course, ORI graphics flag to true because I want the image returned. And then what happens is it returns this job ID. So this is important. This job ID is what you'll use to pull the status of the job. And you'll do that using the RQ job status function. You'll pass the job ID in there. And what I get back is the result location, or this indicates that the job is finished running. And if it wasn't finished running, you'd get a message that the job was still running. So now that I have that result URL, I can fetch the result using RQ job result. And I do that just by passing the job ID and specifying that I want the output format as XML. And because I set ORA graphics flag to true, I will get the data and the image. And then finally, just to give you a quick look at what the REST API looks like, you can't run that in your OML notebook. You'd need to use a curl client like a Linux terminal or a Postman, but this is the equivalent invocation. I'm sending a post request using curl to the doeval endpoint, specifying the script name, random red dots, with graphics flag set to true and the service level for autonomous database set to low. And that's the end of the demonstration. So back to Mark.
Thank you very much, Sherry. Okay, so to summarize, why should you use Oracle for machine learning with R? Well, I'll highlight a few reasons. OML for R empowers data scientists and R users with powerful in-database machine learning from an R API, which gives you enhanced performance and scalability. And by running within Oracle database, users can perform scalable data exploration, data preparation, and machine learning, taking advantage of parallelism and even scoring optimizations at the Oracle Exadata storage tier, while using familiar R syntax and semantics. The integration of Oracle database with the R environment makes it easy for users to deploy machine learning models and user-defined R functions from SQL, and on autonomous database, also REST endpoints. And this simplifies data science projects using system-provided infrastructure for invoking R. And of course, we have Oracle database and autonomous database themselves, which offer many advantages for data management. So I would appreciate if you could let us know what you thought about this session. On a scale of 1 to 5, 1 low, 5 high, how many stars would you give this session? Did it meet your expectation? Were there other topics you'd like to see covered or covered in more detail? And please let us know in the chat or the Q&A. And thank you for that feedback. We're seeing over 50% at 5 and about 40% at 4. And so if there are other things that you would like to see us talk about or explore in more detail, please do add that to the chat or the Q&A. And thank you very much for that feedback. So before closing, I'd like to briefly mention the R Consortium, a vendor-led organization that promotes the R language and leads initiatives in support of the R community. It's committed to help evolve the R language by identifying, developing, and implementing infrastructure projects. And if you use R and are interested in participating in and shaping the R ecosystem, check out the R Consortium website at rconsortium.org for more details and consider becoming a member. For more information on OML, here are a few resources, including blogs, additional code examples, and documentation. And on autonomous database, the OML Notebooks templates include over 35 notebook examples using the transparency layer, the in-database algorithms, and embedded R execution. So we encourage you to check those out. These same notebooks are also available on our GitHub repository shown at the link here. And we encourage you to take OML for R for a test drive on autonomous database at an instance near you. And with that, are there any questions, any additional questions that we should address? We did have a couple of questions. I just want to highlight. One had to do with, does OML services support OML for R? Well, so OML services is one that deals with deployment of in-database models and ONNX format models. So if you have an in-database model, whether it's produced from SQL, Python, or R, you can export that and import that into OML services. If you have third-party models that were produced, Python, R, and they can be exported in ONNX format. Then for classification, regression, and clustering models, those can also be imported into OML services. There was another question about, what's the guidance on which language to use for OML? Is it, SQL, Python, or R, or just user preference? Or is there some obvious advantage for one over the other? And, that's really a great question. For the most part, it is user preference. I mean, if you have data scientists, they are comfortable using perhaps Python or R and would gravitate towards that. If you have folks who are more familiar with Oracle database and just SQL users in general, certainly they would gravitate towards SQL because Python and R wouldn't be as natural for them. However, there are a few cases where there are some functionality differences, at least at this time. And so one example might be that in the case of R, OML for R supports dates today. And OML for Pi will be adding support for dates later in the year. So that might be a consideration. Another has to do with, even visualization. SQL obviously does not have a visualization component to it per se. I mean, OML Notebooks offer some there, but many times you want the visualization that's available through R or Python. And so that would be another reason to perhaps mix and match in your notebook, perhaps some SQL invocations with R and Python, leveraging visualization libraries. And the question was also, will this notebook be available? We can post that to our GitHub repository. But as I mentioned a moment ago, that we do have the notebooks that are available with Autonomous Database immediately accessible there through the OML Notebooks template examples and also in our GitHub repository. So a few more topics that folks would like. Using R for SQL tips would be good. Given a sequence of R commands, what considerations are there for doing the same from SQL and vice versa? That's a great idea. And the R functions in ORE and the RQ functions are not quite the same. And yes, there are differences between the embedded R execution functions from our on-premises implementation that you may be familiar with for ORE from the past, and what we have available on Autonomous Database. And this is because there actually is a fundamentally different implementation on Autonomous Database for embedded execution compared to what we are using for on-premises and database cloud service. And because of that difference, there was a need to modify the API for that. So I would encourage you to look at that more carefully. And let's see, we have one here. Will this deck be available? We can certainly make that available. And if you want, you can reach out to me directly at mark.hornick@oracle.com, and we can get that to you. And I couldn't find how to start from scratch. Okay, so there are a number of URLs, basically documentation that you can access, and Sherry highlighted that she'll send a few out to get folks started on that. So that's all we have for questions. Then again, I thank you very much for your attention today, and until next time.